Hello, hello. Day Daddy here again, and just want to say, as always, thank you guys, and I really appreciate the interest in my channel. If you do find the content helpful to you, I really appreciate it if you guys would hit the like and subscribe button. Um, anyway, now that we've got that out of the way, let's do part 2 in the series, and we'll be talking about. We've already talked about. An overview, which was part 0. Part 1 was just gradient descent. And now we've moved on to really the workhorse. I said that gradient descent was a backbone. Well, this is the workhorse. This is kind of what everything else is built on. So we're talking about SGD, Stochastic Gradient Descent. And I just want to take a minute, as always, to go over my references, and I do use closely the textbook from Dr. John Miller at UGA. It's linked right up here, and specifically this optimization content we're going over is talked about in Appendix A, starting on page 619. Just want to give credit where credit's due. I think it's a fantastic textbook, and I highly recommend that you guys go through and look at it, because it is what I used and kind of base a lot of my things on in this series. Okay, let's hop into stochastic gradient descent. And just again, I want to highlight a video I think is great, has some really great visuals for this. Again, surprise, surprise, it's Josh Starmer with StatQuest, and it's on SGD. I like his stuff because it has a lot of really good visuals. I wish I had the time to do stuff like that, but I just don't, unfortunately. And besides, I think the notebooks, especially with code, are more helpful because you can just run them directly. Anyway, so what is stochastic gradient descent? How is it different? And we touched on that a little bit in the overview in part 0, but basically, the only difference between gradient descent and stochastic gradient descent is the fact that now, instead of taking the whole training set, we're taking a randomly sampled portion of the training set. And we talked about that, and I have a nice visual example in the overview. So if that doesn't really make sense to you, what I mean by randomly sampling, definitely go check that out. It explains it pretty well. But basically, all we're trying to do is we're trying to take that training set, and then we're trying to cut that down and only work with a portion of it, because that saves us on computation. And the next question for stochastic gradient descent, or SGD, is how do we update? How do we update our parameters? And I talked about in the overview as well. You can do it with every data instance. So if you had a matrix, it would be every row. Or you can also update based on mini batch, which is what we'll implement here today. Is a mini batch approach. But basically, it's just this addresses some of the computation. We talked about why can't we use linear algebra to solve all our problems? Well, too computationally intensive. Well, as it turns out, pure gradient descent is also more computationally intensive than we would like. So we use gradient descent to make it even less computationally intensive, because now we can only use a portion of the training set, and we only update once every batch. So that's benefit, save us in computation. However, where we get some benefit, where we get better by having to do less computations, we also get worse because we introduce noise into our data. When I say noise, it could introduce noise, maybe not necessarily would, but because we're not using all the data points anymore. So what do I mean by introducing noise? And I drew this example because I think this kind of highlights it pretty well. But basically, let's say we had, from kind of to repeat the last example, we have these points, and it forms a curve like this, and these are our initial points, and this in red is all of our data, and we want to take a random sample of that to create our batch. And this is kind of a good way to show that as well. But here's our all of our data, okay? And now we're only going to take 4 pieces of it, or 4 rows of that data. So 1, 2, 3, and 4. And if we plot that now, it has a similar shape, but it's not necessarily clear what's going on and clear how we can get from here to the optimum solution. So, and what if we had these 4 values here? Well, that wouldn't look anything like the original shape. So in this way, it introduces some noise. It makes it harder to figure out what the optimal solution is when we only use portions of the data. So, and we're going to see this actually in the end, because remember how in the last video it was a nice smooth line, nice smooth descent to the asymptote, where we had the minimum value. But in this case, it's not going to be like that. It's going to be jerky, and it's not going to be super clear. There's going to be a lot of oscillations that happen, and that makes sense because we're not using we don't have as clear of a path as we once did. So hopefully this makes sense to you. I believe that Josh Starmer covers this as well in a little bit, but I may be wrong on that. Anyway, this is the point. I mean, if this isn't clear, leave in the comments, and I'll try to do a better job of explaining this. But I hope this kind of makes it clear to you guys. Why we introduced noise and why that's important. And you may be asking, well, Spencer, why we do this if it introduces noise? Well, it's better. I mean, it still works. So if it still works and we can reduce our computations, then great. So again, it looks weird. It just won't be as clean, but it still does work. And we just need to make our algorithm a little bit more robust to handle this noise. Okay. So I believe all of this just kind of talks about that. So we talk about mini batches. We talk about all this stuff that we've already kind of touched on. So I'm just going to skip over this for now. Talks about this as a foundational algorithm. And there we go. I just say basically that this is a core algorithm, and then perceptrons is kind of the start of neural nets. So we're going to integrate those two together. So our goal for today is we're going to implement SGD, and we're going to implement that using a perceptron. So we're going to try to optimize the perceptron using SGD. It's okay. So I try to draw a diagram, and this, okay, so I did explain this. I figured I did somewhere. But basically, this is what this looks like, or what this whole process kind of looks like, at least in our case today. So we're going to start out with some training set, some list of X and Y's, and then we're going to randomly select, and this is going to be divided into subcolumns. So maybe X1, X2, X3, so forth. And then we're going to grab data instances or rows out of this table, and then we're going to assign those to a mini batch. And then we're going to keep doing that. So once these have been used, we're not going to use those again. We're going to use, say it's 3. We're using three samples or 3 instances for our mini batch. Then we'll go pick another 3. So this is another one, and maybe there's one down here, and there's one down here, and we use those 3, and we keep doing the same thing until we've used all of the data in our training set without repeating. So we don't want to use the same data in two sets. We just want to randomly select all of the data in different mini batches so that it's all used one time and the full training set is used. Okay, so that's the iterations that are happening here to create our mini batch. And then we have our mini batch, and we need to split the data into X's and Y's. So we've kind of drawn that here, but so the first number of inputs of our instances are going to go into the X, and then whatever our target variable is going to go into the Y. And then we're going to calculate our gradient as we've done before. We're going to update the weights as we've done before. And then we're going to go back, and we're going to go grab another mini batch. We're going to do the same thing, and we're going to keep doing. So imagine this is the inner loop, and we'll see that later. But this is the inner loop. So this is going through the mini batches, and then there's an outer loop that's going through the training sets, or full iterations called epochs. So you have these two things kind of working together, and in our case, we're going to update the weights for every mini batch. We're not going to do it for every data instance. You have another loop inside of this, if you wish, that would do it for every single instance inside of the mini batch. But for us, we're just going to update it once for the mini batch. So hopefully, again, that makes sense, I hope. And again, if you need more explanation, leave me a comment, and I'll try to do a better job. But I think this is pretty clear. Okay, so now let's hop into the code. So perceptron code with SGD. You need a couple imports here. So numpy, as always. Wow, I have numpy twice. That's interesting. I'll correct that. But I think the second one's supposed to be pandas is PD. So let's just go ahead, and I don't think we need pandas in this case, but you know, I find that when you're doing data science, numpies and pandas are just about always a good idea. So there we go. We'll use those two. We need TensorFlow just for the activation functions, and I think I'll cover this somewhere else as well. But basically, Keras has this nice storage capacity where it will store activation functions for you, and you can just call by saying like activations dot sigmoid or tanh or whatever the case is, and that just helps us from having to actually hard code these values every time we want to use them. So that's why that's helpful. And then math we need for a couple things. Let's just select our kernel. So we can initialize all of this stuff, make sure that everything's working. And just as a side note, I'm using a Mac M1 for this, so I actually had to make a special, like, download Miniforge and do a bunch of special things because the processor, the M1 processor is significantly different than what's been done in the past, and TensorFlow really, for a lot of things, isn't really built to work with it. So that can be a challenge. If it is, and you're having trouble, you know, getting TensorFlow installed and using it with your Mac M1, let me know, and I'll recommend some videos, or I'll do my own video of how to actually get that set up for you guys, so that you can use it. But this, as a aside, this did take a little bit of work to get TensorFlow working with the Mac M1. There's some particular versions you have to use and some things you have to actually do to get it set up. It's not necessarily as easy as just plug and play, or at least it wasn't for me. So anyway, let me know if that's something you're interested in or having trouble with. I'll try to make a video on that, but just drop some something in the comments, and I'll check it out. Okay, without further ado, we're initializing our data. So here is our, you know, x and y. So it's this, and essentially we're doing the same thing here. We're just breaking into x and y. So we have our x's and our y's, and then we're initializing our b, our B matrix, and I don't have it, you know, listed out here what that exactly is, but that's, we talked about that in gradient descent. But that's these are our weights, or our update parameters. And also, I'll leave another link to the perceptron video where we go over what this is and what it means. But basically, this is what we are updating. Okay, we want to iteratively make this value as good as it can be, so we can arrive at an optimal solution. All right, so we have to find SST, and this is a function I've used elsewhere, but basically it just gets, we provide it the y's, and it goes through and it finds the mean of those y's. So this is basically going to be a vector of y values. It's going to go through and it's going to find that mean, okay, and then it's going to say for every value in that array, we're going to subtract it from the mean, we're going to square it, and that's going to give us our squared error, and we're going to sum that. So we're going to sum all of those errors together. And the reason this is important is because when we're finding r squared, we have to know what is the maximum possible error that we have in our set. And if you think about it, if we take the mean of every y value and then we subtract every y value from the mean, then there can be no larger amount of error. Like if we summed all of those, there can be no larger amount of error. The every value minus the mean summed is the maximum possible error that we can have, you know, in this set, or in this set of y's. So that's why it's called the sum of squares total, because we can't have any more error than that, and it makes sense conceptually, you know, if you think about it. And again, if this doesn't make sense, I can, you know, put something up, you know, visually to show this, but or if you don't care, you can just take my word for it, and you know, we can move on. But this is just going to help us calculate r squared later. All right, and now we have SST. And all we're doing here is, this is a funky, this output's funky. It has like an extra couple brackets, and all we're doing is we're just taking the actual number out of this weird array because we don't really care about it, and we just want it to print or have that number as a float. So that's all we're doing here. Okay, So let me initialize this as we go, so I can just run it when we go later. So that's initialized. All right. And then this we need to initialize as well. Okay. And now this is where stuff gets a little complicated. So this is where we're assigning batches. So this function, we have two ways of going about this. So this function just assigns a list of the data instances we want to grab. So basically assigns what index positions or what rows we're going to get for each batch. So if we go back to this visual here, it just assigns, so say that we had 10 values, okay? It just says, hey, for the first batch, we're going to get index row 2, row 5, and row 7. Okay, and then it just generates a list of batches of size 3 of this total set. That way we can just say, okay, all right, what's the first batch? And then go grab those rows. And then the second batch and go grab those rows. And we can make sure that we use all of the data and we don't repeat it. So that's the goal of this code right here. And we do that by we pass in the data, so the X and Y, and then we say, okay, and we patch in the batch size. So for example, if we want our batch size to be 5 and we have a number of instances or rows of 10, we're going to have 2. So we're going to have 2 batches. Okay, and then this is just the ceiling because, sometimes it's not easily divisible. We have to worry about remainders. But we won't worry about that in this case because I've made sure that the data is easily divisible. But this should work even if there's an odd number or a weird number of data points. Anyway, okay, so now we are initializing a number of choices. We're saying, okay, we want this many data points based on how many rows we have. Okay, so we're saying like this is how many possible choices we have. We have 10 possible choices, and we're just saying this is a list of those choices 0 to whatever the maximum choices is. In this case, 10. And then we're saying, all right, we want to randomly choose values from this. So for example, if it was 10, maybe we choose 1, 2, 3 or 1, 5, 7 or whatever the case is. And then this is saying, do we want to replace them or not? And we do not want to replace, otherwise we'll end up getting the same values. And eventually we want to run this list out. So, all right, so then we do that. And then we are just splitting, what are we doing here? What is this one? This is the random list that we just created. And this is just going to generate, that number of choices in one large array. But what we want to do is we want to break this from one large array into subarrays. So for example, let's just do it here. So if we have one large array of like 1, 2, 3, 4, 5, 6, 7, 8, and let's just assume, or 9, 10, holy crap, that was bad. Sorry guys. 9, 10. All right, and then we want batch sizes of 3. Well, it's just gonna split this original list, and it's just gonna split it into subarrays of 1, 2, 3, and so on and so on. So that way we know that okay, these are our batches, and this is batch 1, batch 2, batch 3. Oh my goodness, I'm so sorry. It's very hard to draw with the mouse. Batch 3. All right, and you get the idea. And it's going to go on, and then we'll have one. If it's not easily divisible, we'll have one batch that has less values, or we can just maybe even throw that. I mean, in some cases you can throw it away, but for us, we'll try to use it and just use it as a smaller batch at the end. Okay, so that's how we get our batch list, and that's how we actually generate and make sure that we're going to use all the values correctly and all that stuff. And then we have another function that actually gets the values, because all we've done is we've just said what values we want to get, and now we actually need to go get those and put those in a list. So that's basically all we've done here is we've said, okay, here are the values, and then we want to actually go get those values in this function. So I hope that makes sense to you. Okay, and now we need to update our weights, and this is and in future videos, I make this a bit differently, but in this, since it's so simple, or it's more simplistic than the other cases, I just smashed these together and made it into, so everything from here to here, we're getting the gradient. So we're doing the same thing, the perceptron, where we're getting our activation function, our pre-activation function, we're activating it for our predicted y's. We are taking, we're getting a negative error vector. And then we are getting our correction value, our delta vector, okay? And then we're we're dotting that back with our original inputs to get our gradient, and then we're updating the value based on the learning rate, and we're getting those new, before it was inputs, in this case it's weights, and we're getting our new weights for the next iteration. Only difference now is we're gonna keep track of our errors so we can plot them, and we're gonna return the updated weights and the sum of the squared errors. So, and this is better explained and more explained in depth in the perceptron video. And I'll link all these links I talk about and things I'll make clear in the description, so you guys can easily find them. All right, and this is important. We want to set our hyperparameters. So again, in this case, I'm just initializing. So B, our vector of weights, I'm initializing this as new parameters, just so that every time that we run this, I don't have to go back up to the top of the notebook and reinitialize the B vectors so we can start over. Just makes things easier. So you don't have to do this, but I think it makes your life easier. I'm just creating lists. So lists to catch all of the SSE values, and then the R squared values as we go through, and then the list to catch the the number of iterations, so we can plot them all at the end, and we can actually see how this looks. Okay, and again, we are getting SST. We only need to get this one time, because this doesn't change. This is dependent on the actual y values and their means. So we only should calculate SST one time. We don't need to put it in a loop. So we're just calculating it here so we can have this SST value stored, so we can calculate as we go. We're also setting our max iterations at 100. You can set this whatever you want. I think 100 just looks nice for the graphs. Batch size, again, depending on your data set, you can adjust this. Since I only have, I think I put 10 row instances, I just put a batch size of 5, so it would work nicely with 10, and we only have 2 batches that we're creating here. And then I have an eta of 1, and this basically is just essentially setting it to 0, or it is not being really used, and this is the tunable parameter, so we'll adjust this and we'll see how it actually changes things, but for now I just kept it at 1 to keep things simple. Okay, and then now finally we have the structure, I guess you could say, of SGD itself, where we have the outer loop, which we talked about before, which handles the iterations for the epochs, and this is going to go from 1 to the max iterations. And then so every time we do that, every time that we have an epoch, we need to make our batches. So in this case, this is not getting the values. We're delineating how we're going to break up the training set into batches. And we already kind of addressed that. And now we're saying, okay, 4 batches in batch list. So essentially it's going to be a list of lists, remember? So we're going to take one batch and it's going to have, row instance 1, 3, and 5. And then we're going to go and we're going to get the values associated with 1, 3, and 5. And then we're going to store those, or it's going to return an array of arrays, an array of arrays of each of those values. So this is going to be the x values for batch 1 and 2 in our case, and then the y values for batch 1 and 2. And then we call the update weights function, and then we're going to pass in those, basically the data, the mini batch that we need. We're going to pass in the parameters, or in our case, so remember we initialized b as new parameters, so that was our weight vector. So we're basically going to pass in our weights, and then the learning rate, which we set here as 1, okay? And then that's going to iterate, and it's going to update for however many iterations we set. And then we're going to append the iteration number, so 1, 2, 3, 4, all the way to 100, and then we're going to append our error term, so sum of squared errors, and then we're going to append the r squared, which, like I said before, is just one. It's just a formula out of the book: 1 minus the SSE over the SST for r squared. So there we go, and that's really all there is to it. Pretty simple, but pretty effective. And let's run the whole thing now and see what we get. All right, cool. So as we can see, so comparing this to the first, to gradient descent, we can see now that there is a lot of noise. You know, like I said, it's not a smooth path all the way down, you know, to the optimum solution. And forgive me, I know we're using two different examples here, so it's not like the same 4 and 2 we were looking at before, but you know, it should still illustrate the point that now things are jerky. There's a lot of noise because we've introduced more uncertainty into the data. So again, this is just our errors, and we can see the errors are decreasing, you know, but sometimes they're better, sometimes they're not, but they eventually line out almost at 0, which is good, which means that we are able to really fit this data set well. And then again, our r squared, it doesn't get quite to 1, but it approaches 1 because we're minimizing our error almost to the point where we don't have any anymore. So anyway, this should make sense, and this should really kind of drive home the point I was trying to make about the noise earlier. And then finally, again, I said I wasn't going to do a long video. I don't know how these videos always go so long, so I do apologize. But I just want to do one more thing. I want to show you the learning rate. The learning rates, again, it's important. It's very important. So let's just play with learning rate a little bit so we can see what it actually does. So there we go. Okay, so we adjusted the learning rate. We adjusted it really small, and now this just looks like noise. And again, it's most likely because we don't have enough iterations where we can actually see what's happening. So if we change iterations now from 100 to 1,000, let's see if it looks good again. And then again, I'm trying to keep this short because, you know, I don't waste all of your time, but hopefully, okay, there we go. So yeah, we can see that now we're starting to get, we're starting to approach or get closer to that, that same error that we had before. Although again, it's very, very noisy to get there, right? So the learning rate, or adjusting an optimal learning rate, can really, and we'll just do 5, for example, and we'll put it back to 100. We'll see what that looks like. You know, just to kind of see what these things do. And again, okay, so 5 works. A lot of weird variation here that can happen, but you get the idea. Adjusting learning rate will adjust how fast this thing converges. It converges really fast, so it gets down there really fast, but it has a lot of variability. So again, up to you. You guys can play with this if you want, but I just wanted to show those points and impress upon you how important the learning rate actually can be. So anyway, guys, hope that you found this useful. As always, you know, if you did enjoy it, or if the content was helpful to you, you know, please consider you know, liking, subscribing the video. I'd really appreciate it. You know, it helps me provide you guys more quality content. It helps me grow. You know, and also please feel free, and I encourage you to give me feedback on, you know, how these videos are, and if there's, you know, anything I can improve upon, or things you'd like to see, or, you know, other videos you'd like me to do. All those things would be great for the comments. So don't be shy there. Anyway, guys, thank you so much for your attention and for watching my video, and hope you have a great rest of the day. Bye-bye.